Hi everyone. Today we're gonna look at what the subsequent uh, course is going to look like, what we're going to be looking at throughout the semester, throughout the rest of the 4 weeks. um, so essentially, what we want to gain confidence in throughout this course is understanding how systems work, specifically electronic systems. How can we miniaturize these systems, and how can we then embed them into fabrics like so? So um, I'm just laying these out here so you guys get a brief idea as to what the overarching goal would be. So most of you would be familiar with uh, a board like this. This is like a Arduino Uno. You can pick it up from pretty much anywhere. Um, and these are most of its IOs over here, inputs and outputs. You plug it in from here, give it power, program it, and yeah, that's your development board. And then you have small devices like this. This is essentially an Arduino as well. So you can see over here. Um, this is an Arduino. It's an ATtiny 85. You can read on the chip, ATtiny 85. And this big thing here is a buck converter or like a voltage regulator. So you give it in 5 volts and it, or any kind of voltage input, and then it will give you an output of 5 volts. But essentially, that's your main, you can say, computer or processor over there. And then we're gonna go even tinier with this thing over here. This is an ATtiny 1606, or I think it's 80 mega, or I'll double check with that. But as you can see, this thing is super small, and it offers much more uh, capacity and much more capability than the ATtiny 85. So uh, how we're going to go about working with these tools and devices is that we're going to start off by learning how we can develop on the bigger board. So we're going to spend a week on developing on the big board. Then we're going to spend about a week miniaturizing it to something like this and seeing how this works out on a variable. And then once we have gained confidence working with this, we're going to move on by deploying really small chips onto fabrics like this, like so, and adding more capabilities like sensors and interfaces, inputs and outputs. Just to give you guys one more example or another parallel to this, let me just pull out the touch sensor here. So that's a touch sensor, and just like the computation, what we're going to be doing is we're going to be pairing up the big sensor board with a board like the Uno, and then over the course, as we get more comfortable with these devices and working with them and interfacing them, we're going to move down to smaller chips like so over here. This is also a touch sensor. This is a 1 key touch sensor, so there's only one input, but this one is a 12 key touch sensor. And if you can interface this with this, you could have like a mini touch interface. Let me just show how small this is. There it's the same size as a 3 by 3, 3 mm by 3 mm. And the whole goal of practicing soldering and knowing how to use flux would be to eventually be able to make these really fine connections. Again, maybe not all of you will get there or want to get there, but it's just making you guys more aware of what are the possibilities and how far can we push uh, these electronics and these devices and make, smart objects or merge them with fabrics. That's all. All right, let's jump into our first, um, you could say, tutorial for how to work with this Arduino Uno and our touch sensor. And what we would like to do in this first project is just set a baseline, a test bed or a bench test for how we can interact or how we can join different sensors to microcontrollers like this, and how do we generally read inputs from them, and how do we output and signal things, how do we communicate between sensors and outputs and digital devices. So we're gonna just get a look briefly as to what the Arduino Uno is and what it can do. All right, let's put it here and look at it. So here we have the USB port that can program, that can power and program this entire board. What you need to know is that the USB ports are limited to 5 volts and 500 milliamps. So you can't have like heavy loads on these outputs over here. So that's something that might be important slightly later on. But as far as LEDs are concerned, LEDs are pretty low power consumption devices. So you can have LEDs here as much as you want, but you can't have like a motor. A motor is going to pull up probably more than 500 milliamps, and you're going to fry this chip here, which is the interface between the USB and between the chip, and then these, and then the main Arduino or ATmega 328P. That's the chip. So, okay, let's look at what the board has. You're going to see here a row of inputs and outputs, and then you're going to see a row over here, and then a small row there. This one is all your digital input outputs are over here. These are your analog inputs, and this is power. What digital essentially, this is the chip. This is the ATmega 328P, and it's sitting inside like a socket. So in case you burn this or you damage it or you fry it, you can just remove this and get a new one, and reuse the board. You can power the board in different ways. There's a 12-volt connector here that I removed, but yours is definitely going to have that. So you can plug in one of these up to 12 volts, and it's gonna your board's gonna be powered from the outside. The other way to power it is obviously through the USB. There's a third way to power it, and that's going to be through VIN. But you have to make sure that it's always up to 5 volts and not more than that. And at a minimum, it has to be, I think, around 3.3 volts for this thing to power up and work. So here we have our main power in. That is our translator. And what that does is that whenever you want to communicate with this chip, because it's pretty much low level, and you need to have this interface in between. So this communicates with this, and then this communicates with this. Yeah. Now we're going to look into like what these pins mean. What is digital? What is ground? What is in power? What is analog? What is VIN? Ground, 5 volt, 3.3 reset, and yeah. Essentially, all the digital pins, they come in 2 flavors. So you have plain old digital, and then you have PWM. And PWM stands for pulse width modulation. Pulse width modulation. It's simple. It's it's not that simple, but it's simple. So what digital is essentially highs and lows. So this is your waveform coming out of any one pin on the digital line. You're gonna have, they're usually in the zero state. Whenever you define a pin, it is in a zero state. That means it's at 0 volts output. And as soon as you declare a pin to be high, it's going to give you 5 volts or whatever you're feeding it. So if you're feeding at 3 volts or 3.3 volts, that's going to be your high at a digital out is going to be 3.3. So what we're doing is so that's how the digital line communicates. So it's either high or low, or high or low. And the width of this high and low is pretty much fixed in a digital output mode. So if your pin has a fixed width, and that width is controlled by a delay function. So your digital pin can be in two states, 0 and 1, and you can either read or write to a digital pin saying you need to be 1 or you need to be 0, or tell me if you're 0 or if you're 1. So that's what digital read and digital write means in this Arduino context. And as you can see, this is what the waveform would look like while reading or while writing. In pulse width modulation, so pulse width modulation is, you can say, like a special function. And let me show you guys here. Pulse width modulation, or PWM, is only on the pins that have a small wave right next to them. So that's pin 3, digital pin 5, digital pin 6, digital pin 9, 10, and 11. So 13, 12, 8, 7, 4, and 2, and 1 and 0, so they don't have pulse width modulation. So you have 1, 2, 3, 4, 5, 6 PWM pins on this particular board. If your application uses more PWM pins, we're going to look into what it can do in a bit. But if your application uses more PWM pins, you can move to a bigger Arduino. And we looked at this small Arduino earlier on, the ATtiny85. This one has 3 PWM pins. So out of this entire thing, you can use 3 pulse width modulation pins. Pulse width modulation is a super fun function, because what it lets you do is you can change the width of the pulse and manipulate it any way you want. So this is what you're doing. You're playing with the width of your pulse here and here, and so let's start by wiring this up. What I'm gonna do is I pulled out 3 wires from here, and I'm gonna connect. I like to keep some conventions, like red being positive, black being negative, and then any other color being the signal wire. It's just easier to not mess up. So I'm gonna just trace. Red goes to VCC and black goes to GND. So black, red, and then signal. I'm going to put these 3 in here. And then on the other side, I have red and black going to 5 volt and ground. And brown, I'm going to put it on, let's say, 12. So I'm not going to put this on 13, and I'm going to explain in a bit why. But 13 is connected to an onboard LED that acts as an output for you to see. whenever I get an Arduino board, first thing I do is I plug it in, I open up the Arduino software, and I go to File, Examples, Basics, and Blink. So Blink is my just to test and make sure that the board works, the uploading works, everything is connected. I hit upload, and what this upload does is that what Blink does is that just makes pin 13, which has an LED, which has an onboard LED attached to it, flash on and off for 1 second. So it's on for a second and then off for a second, and this program or this loop keeps running. This tells me that the program was uploaded onto the chip, the LED works, and everything's being powered. So if you don't have an LED, you can always, to debug or to, also what debug means is to get rid of any problems. Don't be confused by that word. So to debug or to troubleshoot, this LED is super helpful. And also, if you just don't want to add another LED, there's always one on board to make sure and check if what you've done works or doesn't. So I'm going to pull this out. I'm going to reconnect these. We got ground and 5 volt on the power rail. And I'm going to connect this to 12. So what I want to do is I want 12 to be reading the signal off of this. So because this is a digital IC that converts capacitance to either a high or a low, that means if I'm touching here and it senses that there's a change in capacitance, which I have, which my skin has as I touch here, it's going to, this brown wire or the signal wire is going to be high. So it's going to send 5 volts down this line into pin 12. And if it doesn't sense anything over here, it's going to constantly send a 0 down to 12. So it's going to be a digital low. I can, we're pretty much done with the wiring now. We're done with the hardware part of it. And now we're going to jump into the software and see how we can make this all work. So as soon as I connect that, you see that this tiny board has a status LED just to show that you've powered it and everything works. And I'm going to upload the program that I've put together, which is super straightforward. It has, I have an input here, which is touch, and touch is on pin 12. I have an output, which is LED, and LED is on 13. And I have a variable that is called the state. So what I'm doing is I'm reading, so digital read touch, and store whatever touch has in state. And so if digital reads touch and touch is high because I'm touching here, is state, the variable state becomes high. And if it's not, then the state remains low, which is 0. So and then the next thing that I'm doing is I'm seeing if the value of state is equal to 1, which is high, then pin 13, which is the LED, write digital write on that pin and make that high. And whenever you put else right after if, what it means is that it just does the opposite. So if state is not equal to 1, then digital write with an LED low. So what I'm doing with this program is if I touch here and this brown signal is high, the LED on the board should light up. And if I'm not touching and the signal wire is low, then the LED should remain off. Let's upload this and see if it behaves as we programmed it. All right, program has been uploaded. And as soon as I touch the board, LED 13 lights up. I'm going to bring this up closer just to make sure you guys can see. So as soon as I touch it, LED 13 or digital 13 goes high. That's that. That's your first assignment or first project done. An extension to this would be, let's say we want two outputs, and here we have this motor, this mini vibrating motor, and we want to attach it to the loop so that as soon as we touch this, not only does the LED light up, but we also get some vibration on this motor. I'm going to strip the ends of this. And we're going to put this, let's say, on pin 8 and pin and ground. So we have 8 and ground. Let's just adjust the code a little bit. Let's add another output, which is motor and pin 8. So this motor consumes about 40-50 milliamps. That's still below 500 milliamps that this port can provide. So we're good running this motor. It's on pin 8, and I want to give this pin a digital high. Pin mode should be output. Okay. It's super precise. You can, this width can be adjusted to like nanosecond timing. So up to a few nanoseconds, I think. You can control the timing and the width of this pulse. This is used in many applications, like controlling servos. So whenever you have a servo, let me quickly grab a servo. Servo motor. So that's a servo motor there. And you can see it has 2 power pins, which are the gray with the brown and red, and then yellow is the signal pin. And yellow you cannot connect to a digital. You cannot connect it to a digital pin. You have to connect this to a digital with PWM. So you can then send signals to the servo, and it will start moving left and right. Yeah. What we are going to look at today is going to be a really simple input, which is our touch sensor here, sending a signal to one of these digital pins. And then we read the digital pin and we write to a digital pin to give us feedback. So we're essentially going to take an input from here, and then through one other digital pin, we're going to send an output to see whenever we have touched this, there should be a light that turns on and off. On this side of the board, on the power side of stuff, you're going to see there's a VIN that is a voltage in. There are 2 grounds, and then there's 5 volts. This 5 volt is more of an output 5 volts. So you can use this to drive different things. Like this sensor here has, it gives you a signal. It has VCC, which is VCC is like positive voltage, and ground is your negative. So let's wire this up. So VCC goes from here all the way to 5 volts. That's how we're going to power this board here. We're going to connect ground all the way here to ground. By the way, if you're out of ground pins, there's a third ground pin here as well, in front of 13. And then we're going to connect signal to one of these digital pins over here. It could be pretty much any one of these. I won't use 0 and 1, but from 2 up till 13, you can use any digital pin. All of these pins can be digital, but 6 of them can be pulse width modulated. Let's verify if the program is correct. If it is, let's upload. All right, so we have a problem. So as soon as we touch it, the motor goes high, but it doesn't go low when we stop touching it. So we need to also have the same code with an else. Let's do that, upload, and it should work now. Yep. So as we touch, the motor spins, and as we let go, oh, leg came out. There we go. So that's that. Yeah. These are all, so far we've played with digital. Next we're going to look at analog, and then after that we're going to look at PWM. All right.